Hello, everyone. Welcome back. Now I'm gonna have a real pleasure, which is to introduce to you all, sorry, a very good friend of mine who's also a leading star in the field of quantum communications in Britain, United Kingdom, all over the world. And his name is Emilio Hugues Salas. Let me introduce him to you all. So Dr. Emilio Hugues Salas received his B.Sc degree from the Monterrey Institute of Technology and Higher Education, el Tecnológico de Monterrey, in 1997, and his Master in Science as well as his Ph.D. degrees from the University of Essex in the United Kingdom in 2002 and 2008, respectively. Sorry. From 1998 to 2002, he joined Alcatel-Lucent as a product engineer in the Transmission Systems Department. In 2006, during his PhD research, he was employed as a senior research officer, and in June 2009, he joined the Optical Communications Research Group at Bangor University, also in the United Kingdom, as a postdoctoral research fellow. From 2013 to January 2021, he was employed as a research fellow by the University of Bristol in the High Performance Networks Group. Currently, he is a specialist research professional working for British Telecom, where he is involved in the Innovative UK AIRQKD and the Quantum Data Center of the Future projects. He also contributes to other activities aiming at the design of experimental quantum networks. Finally, Dr. Emilio Hugues Salas is a full college member of the UK EPSRC Peer Review Associate College, and he is an associate editor of the IEEE OSA Journal of Lightwave Technology. He is a senior member of the Optica, formerly the Optical Society of America, and the title of his talk is Secure Practical Quantum Networks and Applications. Emilio, muchísimas gracias por estar con nosotros. Un abrazo a la distancia. La palabra es tuya.
Gracias. Thank you very much, Salvador, for this kind introduction. And also for me, it's a pleasure and an honor to be here in this conference, Quantum-Latino. Well, also I want to thank all the organizers of Quantum-Latino and for letting me do this presentation. Well, good morning or good afternoon, wherever you are. In this talk, I will be giving a description of the activities of British Telecom, where I work, and related to quantum key distribution networks. And also, I will talk about some projects related to quantum that in BT we are involved. Just one second. Yes. So this is my talk outline. So I will start with an introduction. I will proceed then with the Qkd trials. I will give some more details. Then I will talk about these quantum projects, which for us are exploratory projects to find out more where quantum is moving or what are the trends for quantum. And then I will conclude this talk. But before I go in detail about these Qkd trials, I want to just talk a little bit about the research and development of British Telecom or BT in United Kingdom. BT has most of the research in Adastral Park in Ipswich, in UK. And well, what you can see here is one of the main buildings of this park. It's called Orion. Or a name after the constellation, and other buildings are named after other constellations. But yes, in this park there are around 4,000 employees. Some of them are BT people, other from Openreach. There are partners, visitors, early careers, or apprentices. So it's a big research that is done in BT for many areas, not only quantum, but one of them is quantum. And a bit of history. BT started as an electric telegraph company in 1846, and it was until around 1980 that BT was branded as BT, as we know it now. And around that time, there were also important milestones for BT, and one of them was the transmission of 140 megabit per second over a single mode optical fiber link. And this link is important because in that link, I will say later that there was also a Qkd field trial, one of the first ones. So, well, also going talking about these milestones and going chronologically, I have here, well, several milestones that happen all around the world. For instance, in 1984, the famous BB84 protocol created by Benedct Brassard was created. 10 years later, Peter Shor created a quantum computing algorithm that was able to find the prime factors of integers, which were useful to break crypto systems such as RSA, Diffie-Hellman, and elliptic curves. And well, more recently, the race for a higher number of qubits by several companies such as Intel, IBM, and D-Wave with 5,000 qubits was achieved, and still is going up. Also, as it was mentioned by some talks from yesterday, that there is a quantum advantage declaration by Google, and then later by a Chinese group led by Jianpan Wei. And well, there is an expectation that in 2025 there will be quantum computers with a million qubits, and that's based on some statements by companies such as PsiQuantum. On the other hand, well, the BT around this time, well, as I mentioned, in 1984 there was this field trial. This successful trial of transmission of 140 megabit per second, and over the same link, which is a connectivity between Cambridge and Adastral Park in Ipswich. The first Qkd trial was established. More recently, there was an evaluation of hollow core fiber, and just a few months ago, there was a launch of a Qkd network in London, and is still ongoing. So, well, I will discuss a bit more about that, those milestones. But well, as you are aware, or most of the audience in this conference are aware, quantum computers are very useful, or they will be very useful once they are fully operational. But also they could be a threat, specifically for the security. So there is a race, a global race on creating Qkd networks, and well, there are countries such as Japan and South Korea that are investing heavily in these secure networks based on quantum key distribution. And well, Japan is aiming to have that secure network by 2025. In Europe, there are very strong initiatives also to create these quantum networks, secure networks, and some of them are the EuroQCI and the OpenQKD project, where not only is the infrastructure but also the applications to secure hospitals, banks, and so on. So there is a lot of work done over these initiatives. And yeah, in Germany also there is a big initiative to create this network secure for the government by 2022. And well, of course, China is world leading in this deployment, and they have a very important objective that by 2025 they will have a nationwide network based on this kind of quantum security. But well, before moving on what these trials, I want to very briefly discuss what is quantum key distribution, since I'm talking about this concept, and I'm sure that many people in this audience know a bit more about this concept. But well, basically we have a transmitter, or ALICE, as it is well known in the area, is transmitting encoded photons from over a secure authenticated channel towards Bob, and Bob retrieves this data, but after filtering or having some kind of discrimination of these encoded photons, which can be encoded in phase, in polarization, or any other way to encode it. So once Bob receives this information, sends back to Alice not the encoded information of the encoded photons, but of the bases that Bob randomly chose. And then Alice then again compares what Alice sent and the information that is receiving from Bob, and then continues sending more data until Alice and Bob have exactly the same data, and then they both generate a symmetric, what is called a symmetric key, because it's exactly the same key in both transmitter and receiver. Of course, this is a very, very light way to explain the concept. There are other processes happening, such as privacy amplification, error correction, and so on, and it all depends on the protocol. As I mentioned BB84, but there is coherent one wave, there is E92, there are other protocols also that are good for quantum key distribution. And well, this happens typically over optical fiber, but there is also a lot of work on encryption, quantum key distribution over the free space and satellite. So that's what I wanted to mention as a concept of QKD. But alternatively, there is also what is called post-quantum cryptography, and these are post-quantum algorithms that are hard for a quantum computer to break. And well, these algorithms were there was a competition that started in 2017, the standard body NIST, and well, there are cryptographers that are evaluating heavily these algorithms, and very soon we will know who are the winners of this competition. So well, that is an alternative. However, well, we don't know who is going to be the winner, and also well, at the moment we know QKD is working, so it's ready. It's ready as a to generate these keys. And well, we don't know also what will happen. There was recently a paper where AI was used to improve the algorithm that of Peter Shor, and well, that might be the one of that will make this algorithm stronger and more difficult to or more useful for the quantum computer to attack any secure network. But who knows? I mean, for my point of view, the best way is to combine QKD with the post-quantum cryptography to create a stronger or more secure protocol and network. Well, now I'm going to discuss a bit more the Qkd trials, where BT has been really active. In 2018, this field trial in between Cambridge and Adastral Park was undertaken. It was around 120 kilometers of distance of this field trial interconnecting these two sites. And as you can see over here, there are intermediate sites called trusted nodes, where the keys were generated, and these trusted nodes were useful to create keys that were easily used for longer links, like the one from here, from Cambridge to Adastral Park. So, however, well, it's called trusted because this area has to be secure, and there shouldn't be any access to any not trusted entity. So, well, this was trusted successfully, and in addition, it wasn't not only for the transmission of these encoded photons for key generation, it was used in parallel with some classical channels, as they are called in the area, or standard telecom channels of 100 gigabit per second. And that was a big achievement, because this is called coexistence of quantum and classical channels, and these classical channels are usually sources of big amount of noise that easily can wipe out all these quantum channel, which are mainly few photons. So to run it, and also it has to this has to happen over the same optical fiber, because it's not practical to each time you want to do a Qkd network to add another pair of fiber all over the city or the country just for this network. So it is easier just to run it in parallel over the same infrastructure. Yeah, here there are some of the results showing the stability and creation of keys during this test. Another big important trial was achieved in the city of Bristol, and that was with this institution called the National Composite Center. That was a big achievement because it is more towards the application. So even though the link was 7 kilometers, and well, for Qkd, I mean, there have been hero experiments with almost 100 kilometers. But what was important is how everything could be integrated and for a practical application. So in this case, this NCC is an institution that deals with materials. They do research of very complex materials, and all this data, they were looking how to send it over any secure link in between the buildings. So that was very important. And also it was very important to see how to integrate it over a field trial where in two buildings in a city had to go through an exchange, a standard telecom exchange to transmit this data in a secure way. So it was a lot of work. There was a lot of design how to do it, and of course, again, this coexistence had to happen because there were few fibers available for this experiment. But that was achieved successfully, and well, that was in the press a couple of years ago. And the recent exploratory test that was done also in BT happened over whole core fiber. And well, why Qkd over whole core fiber? Well, first of all, what is a whole core fiber? Whole core fiber is the standard. Well, we start with the standard single mode fiber. The single mode fiber has a core that is made of silica, and there is a refractive index that allows the signal to go through the fiber. But the whole core fiber is just air. Instead of having a core where the signal goes through, is air, and then that brings some benefits. Of course, to manufacture this kind of fiber is quite complicated, but once you have it, that brings several benefits, such as ultra low nonlinearity, and that is because that allows to inject large amount of power into the fiber. Also, the latency is quite low, and can be comparable to 30% faster than the current fibers. Transmission bands, it allows better performance over other bands compared to the single mode fiber. Is more thermal stable, is less sensitive to thermal variations, and that is good for applications such as timing. Chromatic dispersion is lower, and that is very helpful because that can also reduce the cost of components. So we can again transmit with the non-return to zero equipment or lace modulators and so on, which are cheaper than the coherent usually. And well, that brings a more optimized network with a lower number of amplifiers, and for that, some of my colleagues did some evaluation, some modeling, and they show that 20% of less amplifiers were involved in a network if whole core fiber was used. And well, we did the test, so we proved that it is possible to do this coexistence of quantum and classical channels over a whole core fiber, and we use carrier grade Qkd units. These ones are from ID Quantique. It's a Cerveris unit. And then, well, we managed to input as much as 10 dBms of launch power, which is really high compared to standard single mode fiber that typically you don't go beyond 0 dBms because of the nonlinearities that you can create over the fiber. And also, well, the noise is, well, part of this nonlinearity is affects the any quantum channel. And well, you can see here how even if you have a very large power, the noise can go beyond different the C band, or what is called the 1500 band, goes and also under this band. So that was there is a big interest on this kind of fiber. I mean, not only for VT but for many for on the research area, how to exploit it better. But for quantum, that is, I believe, it's a good option. And well, just very briefly, I want to talk about this Qkd trial or Metro trial in London. It's just it just was launched a few months ago, and it's with Toshiba with their Qkd units. And well, you will hear more about these trials. There is a big engagement or looking to engage with the customers and to show them the capabilities of this type of networks. Now we'll talk a bit more about these quantum projects that we are involved. Some of them, if these are the ones that I would like to discuss with you this time. One of them is called AIRQKD, and that's because it's Qkd over there. So why we would like to do Qkd over there? So the motivation is, one of the motivation is 5G, because there is as many of you are aware, the 5G is there is a big rollout of 5G all over the world, and BT is very involved in this 5G as well. And that's because that 5G can provide bigger or larger capabilities, or the capacity of this kind of networks is higher compared to the previous 4G and 3G and so on. And also the latency is lower, and there is more machine communication. So there are several requirements that 5G is achieving at the moment. And well, there is a lot of expectation in the future with this kind of networks. And well, one big issue is what is called densification, which is the connectivity between small cells to a macro cell. So in a city, with all the technologies that are at the moment, there is a big connectivity, and that can create a problem, a bottleneck. And there are current solutions such as millimeter wave, but that is limited with respect to bandwidth, and to add more fiber. But well, of course, that requires a big investment, and also of money, and that will take some time. So an alternative will be to use free space optics. And since we're exchanging data over the free space, we can add quantum key distribution for the security of this data. Well, that's the name of the project. It's a UK project, which is called AIRQKD. And it is in different layers. One layer is the design and implementation of quantum components, such as single photon sources, single photon detectors, and QRNGs. And for that, we have a very, very strong partner called, it's New Quantum, and is one of the sponsors of this conference. They are doing a really good job designing this kind of components. With regards to the systems, there are University of Herod-Watt and Fraunhofer in Scotland. They are developing the Qkd free space optics Qkd, and they are doing a good job in how to implement that. And where we cannot go with free space optics QKD, there is a company called Angoka that is developing the device authentication units for this extension of the security end to end. And yeah, the part of this project is also to develop use cases. And well, there are two main use cases, which are mainly, well, this figure shows the whole concept, and the aim is to interconnect roadside units or lampposts to buildings and do the security with QKD in between buildings, and with the device authentication units in between vehicles to the lamppost and so on. The other project is the Quantum Data Center of the Future, which is also a very exciting project. And this project is aiming, well, it is not well known how data centers are related to or can be integrated with current telecom infrastructure. And that's very contradictory with what is happening with the actual data centers with the current telecoms, because they are very integrated. So this project aims at understanding this integration, and also to look at the future, how quantum internet can be, well, what will be the quantum internet? Because even though there are very strong proposals and views nowadays, for instance, with teleportation, with QTech, very not long time ago, it was shown that it's possible, this quantum internet. But still, to put it more physical, that's still not very clear. And there are some motivations. I mean, not many groups are working towards this end, and it's just starting. For instance, Equinix and SK Telecom are looking into the integration of these two quantum and data centers, but on the security side. And more recently, there is an initiative in Germany that aims at integrating supercomputer with quantum computers. How I'm doing with time, Salvador? Sorry.
We're doing well, but I think we should start wrapping up so that we can have
Okay.
time for one or two
Okay.
questions.
Sure. So, okay. So this slide is, I think, is already is very. Most of the people on this conference know that the different types of quantum computing to create qubits, but for this project, it was selected photonics, and that's led by the coordinator of the project, which is Orca Computing. And that's because it's using the advantages of using photons for this quantum computing. And some of them are the easy scalability and the low coherence and the operation at room temperature. So these are the partners of this project, and there are the aim is to integrate quantum and classical technologies in a hybrid data center of the future. And well, this is the conceptual and very first proposal of this project, which has a classical data center with racks and servers, and even we added some top-of-the-rack switches, which we aim to have them optical, and that also interconnects to clusters that are with quantum technologies, quantum processors and memories. And then access to this data center has to be done securely, and for that we have a company in Bristol called QEDS that does this kind of technology, quantum key distribution, and to give access to institutions such as this National Composite Center. Well, now I would like just to conclude this talk that mentioning that there is significant progress on quantum key distribution, and it's moving from experiments to commercial solutions. And that's why we are doing some trials in different parts of the country. Qkd is a building block. It doesn't give all the security. It's a building block, and we see it as part of our portfolio of services. But it's a quite strong security. Well, will support all the entire security of any system. there is a need for operators to lead in this infrastructure based on QKD, and these exploratory projects help to look at this future quantum internet, since we can understand better based on this integration of technologies in a data center. Thank you. If you have any.
Thank you very much, Emilio. It's been a real pleasure to listen to all the wonderful projects we're working on at British Telecom. Sorry, there are two questions I would like to pose and briefly answer, please. The first one is, well, both are coming from Daniel Ferrer from AstraZeneca. First one is, in your opinion, what would be the 2 or 3 most outstanding benefits for quantum networks comparing to digital traditional networks?
Well, yes, in my opinion, and I think probably there's many of the community of quantum will think in a similar way, is that quantum brings additional features that the traditional networks cannot provide. So quantum, for instance, there is a lot of work on the timing, on sensors that are way beyond what the classical methods of doing this kind of measurements are achieved. So that is on one end something that can help on this type of quantum networking will be ahead of the traditional networks. We have the protocols also will be supported by now additional parameters from quantum, and of course security is. I forgot. Yeah, I should have mentioned during the explanation of quantum key distribution, is that when there is an eavesdropper trying to interrupt or intercept the data between Alice and Bob, they will irreversibly modify the data. So this non-clonable feature of quantum is not easily imitated in classical networks, and that is one of the big advantages with regards to security. And any other that's the reason why quantum key distribution is information theoretical secure. So these are, I mean, there are more, and that's the reason all over the world there is a big investment in these technologies.
Okay, thank you very much. And the last question is also from, as I said, from Daniel Ferrer from AstraZeneca. It says, are commonly used these quantum networks, these quantum networks of everyday use, or still are they only in experimental phases?
I can tell you about the networks of the field trials of BT. They are still at the field trial level. They are not in the experiments, are in an enclosed laboratory with everything under control. And the field trial is closer to how it should be deployed, and is already there, closer to, and is now exposed to the end user to see how what are the benefits, that they are able to see the benefits of this type of network. There are some of these QKD networks, or at least links, are already available for some bugs. As far as I know, some bugs in Switzerland and some other, maybe in China, they are doing them. But I can, as a network, they are still as a field trial. So this is as far as I know.
Okay, thank you very much. Well, Emilio, thank you very much indeed, and again, for joining us. It's been a pleasure to see you again, as well as to listen to the great topics you've been working on over the last few years. So thanks. Yep.
Thank you very much. Thank you for the invitation, and it's a pleasure to see you again and to see everybody.
Indeed. Gracias. Cheers, and thank you very much. See you later.
Bye bye.
Bye bye. And now let's move please to the virtual space in which Dr. Edibrando Vasquez will talk about his experience entering the quantum industry with IBM Quantum. Thank you very much.